Good evening, everyone. We must apologize for this late start. It's now 9 minutes past 5. Um, Unfortunately, uh, the our host was stuck in traffic and was not able to make it in time. I'm glad to see so many of you here. You have patiently waited, and I suppose the latecomers would be very relieved to know that the class has not started. So, without much further ado, we shall go straight to the work at hand. So today we are doing session 8. Um, and okay, sorry for that delay. I just got lost there for a moment. Okay, so session 8 is quite a large part of this is about counting. I think we have done a little bit of counting at some other times, but will go into a little bit of greater detail regarding counting. And I think there are some other interesting problems apart from counting for today's session. Okay, the first question, as you see here, a square tile is divided into 4 smaller squares, and each square must be painted using one of the colors, yellow, red, or blue. So there are 3 colors. You have to use one of them. How many different tiles can be painted if exactly 2 colors are used per tile, and 2 tiles are considered the same if they can be rotated to look the same? All right, so let's. So in other words, these the 4 tiles, they will be colored in any one of 3 colors, either yellow, red, or blue, and we want to know how many different tilings are possible. All right, so let's just go straight into the problem. Suppose for a start we are using only red and yellow. So you can see here I've got only red and yellow. Uh, of course, red and yellow are just 2 of the possibilities, but you could have had red and yellow, or you could have yellow and blue, or you can have red and blue. There are 3 possible ways of using 2 colors. And then, of course, you can have 3 colors, which can be red, 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 blue, 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 or yellow, yellow, yellow. No, wait a minute, wait a minute. This is not what we want. Okay, let's come back to that. Okay, suppose we use exactly 2 colors, and the 2 colors we choose are yellow and red. Now you can see at this picture here, there are only 4 ways of doing it. And you can see you can have the 2 horizontal, or you can have it like this, or 3 red and 1 yellow. But you must have at least 2 colors. I think that is what is said here. Or if exactly 2 colors are used per tile. So it says that exactly 2 colors are used per tile. So we are now looking at there are 3 possibilities if there are exactly 2 colors, and they are red, yellow, yellow, blue, and red, blue. Okay. Now, so in this case, yeah, you got 4 different ways of doing it, as you can see. You can have 3 yellows and a red, or you could have 3 reds and a yellow, or you could have 2 reds and 2 yellows, and there are 2 possibilities for 2 reds and 2 yellows. No other possibilities exist. If you look around, try to do something, you'll see they are always one of these. And in other words, if it's rotated, like for instance, I could have had this. I could have had the reds here and the yellows here. But this is the same as that, because if you turn it around, you will get exactly the same thing. All right. So there are 4 ways of doing it for red and yellow. And of course, you can expect 4 for each of these situations: red and yellow, Y and blue, yellow and blue, and red and blue. And the question says exactly 2 colors are used. So the answer is 12. All right. So those exhaust all the possible cases. Okay. So that takes care of that problem. Let's now just get on to the next one. Now, this problem here, it says, consider an 8 by 8 empty chessboard with 64 squares. In how many ways can you place 1 black rook and 1 white rook on 2 different squares that are on 2 different rows and 2 different columns? All right, that's quite a mouthful, but let me just recall something that we said some time ago. And at the heart of all these problems is the following kind of a thing. I'm going to try to simplify it. I've done it before, I'm sure. And it's like this. Suppose I've got 3 towns, A, B, and C. And I got a number of roads which lead from A to B. Let's say you got 3 roads from A to B. And likewise, suppose you got, say, 4 roads that lead from B to C. Okay. And the problem is, in how many ways can you go from A to C? Right? Now, the way to solve that problem is, there are many possibilities. I could choose that and go down this way, or I could choose this and go down that way. And if you try to count all of them like this, you'll find it quite difficult, because you might miss out something, or you might count something twice. So there must be some systematic way of doing it. And the way to do it is, you take just this one here. Suppose I take this first road here, road 1. To road 1, if I take that road, then I can go to C in 4 different ways, right? So that will exhaust all the possible ways in which road 1 is chosen. Now, in the same way, for the same reason, if I chose road 2, again, there are 4 possibilities. And if I chose road 3, then again, there are 4 possibilities. So altogether, you've got 12, right? There are 12 possible ways of traveling from A to C. Now, the logical argument is the following, that the first road can be chosen in 3 ways. Listen to this argument. The first road can be chosen in 3 ways. For each choice of the first road, like for instance 1, there are 4 choices for the second, right? So, but the first road can be chosen in 3 ways. So the total number is 3 times 4. That is how you get 12. Because the first possibility, there are 3 ways of doing it. And for each choice of this, there are 4 ways of choosing the second one. So therefore, you have to multiply these two, as we have seen, to get the final answer. Okay, so this kind of problem occurs in many situations. Like, for instance, you could have, what I normally do is I put a box like that, and then suppose I got 2 roads. I'll put a vertical line here, and I say the first road can be chosen in 3 ways. So I put that there. The second one can be chosen in 4 ways, and the answer will be 3 times 4. So I try to fill each box by the number of possibilities I have. How many ways can I fill each box? And then at the end, I multiply all of them together. See? So that is the strategy in all these types of problems. This thing is called the first counting principle. It's in the school syllabus. I think you do it in matric. The first counting principle says the following. If, I'm not going to write it in full, it's time consuming. If you have 2 actions to be performed, and the first one can be done in m ways, and for each choice of the first, there are m ways of doing the second, then there are m times n ways of doing both together. So here you got going from A to C, you're doing that and that. So there are m times n ways of doing the both together. So if there are m ways of doing one thing and n ways of doing another thing, then there are m times n ways of doing both together. Now, you could have had, instead of having only 2 choices, I could have had 3. In other words, I could have had a third town, right? And you could have said, well, suppose there are 2 roads going from C to D. Now, how many ways can you travel from A to D? And the answer is the same logic you use. Because you would say the number of ways from getting from A to C is 12 ways. We just counted it. And there are 2 ways of choosing from C to D. So for each of the 12, there are 2 ways of completing the journey. So there are 12 times 2, or 12 plus 2, ways of going all the way from A to D. So in that case, what you would have had is you would have had a third box, and you will put a 2 there. And you multiply the 2 together, the 3 together, and you will get 24. And that is the total number of ways in which you can travel from A to D. So you would appreciate it doesn't really matter how many roads you've got. Each time you find the number of ways of doing each one of them, and in the end, all you do is do it one at a time, and then you multiply all together to find out how many can you do all of them together. Okay, now there is somebody who is making a mark on my screen. I'm not sure who it is, but please stop doing this because you're messing up my screen. All right, please stop that. Remove your mark as quickly as possible, please. All right, so bearing that in mind, we can answer this question here as follows. Thank you to whoever has removed it. You got a chessboard, and now you have a chessboard that's got 64 squares. So I'm not going to do the whole thing. I should have been prepared for it, but I forgot to bring the chessboard in. But you got 8 columns and 8 rows. All right. So what are you going to do? You're going to place a white rook. A rook is the same as a castle, right? If you don't know how to play chess, it doesn't really matter. But if you do know, it's that little piece which looks like this. Anyway, I'm not going to do that. It's just a waste of time. So you're going to place two rooks or two castles on this board on two different squares that are on two different rows and two different columns. So you will have two castles like this with a white and a black. And so what you're going to do is put a white somewhere here and put a black. You can't put a black in the same column. You'll have to put a black in another column. So you can't put these two in the same row or the same column. Okay, so in how many ways can you do this? Okay, all right. So this is the same problem that we had spoken about earlier, because there are two things to be done. One, you have to place a white rook, right? And then you say, how many ways can I place the white rook? And the answer is, so the white rook can be placed, you got 64 squares. So the white rook can be placed in 64 ways. Right, so once I place the white rook, now I have to place the black rook. And now the black rook can't be placed anywhere here or anywhere here. You're not allowed to place it in the same row or the same column. So now it means you have to place it elsewhere. You're not allowed to use any of these squares. Now, how many squares are here missed out? There are 8 in this row, and there are 8 in this column, right? But you count this only once. So you got 8 plus 7. So there are 15 which are eliminated for the black. You're not allowed for the black. So you got 64 minus 15, so 49 choices, 49 ways of placing the black. So once the white square is placed, there are 49 ways of placing the black, and therefore, according to what we said earlier on, for each choice of the white, there are 49 ways of placing the black, right? So there are 64 ways of doing the first one. So therefore, there are 64 times 49, and that works out to be 3,136 ways of placing the black and the white together. Okay, so the most important thing is that you're multiplying two numbers. The first one can be chosen in 64 ways, and the second one in 49 ways, and therefore you will have 64 times 49 ways of placing both of them together. Okay, so now let's look at the next problem. The next problem says the diagram shows two parallel lines with 6 points indicated. How many triangles can be drawn with the vertices from these points? From these 6 points. So you're going to use these points here as vertices of the triangle. There are how many? There are 6 points at the top. Oh, I'm sorry, there are 4 points at the top and 2 points at the bottom. So how many triangles can you draw? Okay, for a start, you can't choose the 3 vertices on the same line, obviously, right? For a triangle, you can't have 3 vertices on the same straight line, you're not going to get a triangle. So you'll have to choose at least one from each line. All right, now let's do it systematically. So if I choose this as my vertex, let's choose that as a vertex. Or suppose I choose two vertices on this line. Okay, let's do it like that. I got two vertices chosen on that line. Then how many triangles can I draw? Okay. Now I don't really have to draw the triangles, but what I can see is that the third vertex can be chosen as that one. That'll give me one triangle, or that one, or that one, or that one. So in this case here, you have 4 triangles because you got these two, and the third one can be chosen in any one of those, and they'll give you 4 triangles altogether. So that is 4 if 2 in the lower line are chosen. Okay. Now, suppose instead now you choose only one point in the lower line. Okay, so what does that mean? If you choose only one point in the lower line, then I have to choose 2 points in the top line. Okay, so I could have chosen this point here and choose 2 points in the top line. Now, how many ways can you choose 2 points in the top line? I'm going to count the number of ways. Suppose these points are named A, B, C, D. So with this choice, I could have chosen AB. That will give you one triangle, those 2 vertices. Or I could have chosen AC. Right? Just make sure that A is chosen, AB, AC, AD. Right. Now suppose we don't choose A, we choose B now. And then you can have BC and BD, BC and BD. You know, we don't have to choose A now because we've already done that. So that takes care of B. And then as far as C is concerned, you can only have CD. Right? So for this tick here, there are 6 triangles. If I choose that as one of the vertices. Now, I could have chosen this other vertex. I could have chosen this vertex here, and that'll give me another 6. Right? So there's 6 for this vertex, and there's another 6 for that vertex. So if you choose only one point, if only one point are chosen in the lower line, is 1 point is chosen in the lower line, then you've got 12 triangles altogether. Right? For this point, you got 6. For this point, you got 6. You got 12 altogether. So that takes care of all the possible cases. So therefore, the number of triangles that you can draw is 4 plus 12. See? So the way to do that is, you see, if I choose 2, then I count it. If I choose 1, I've counted that. It's not possible to choose none of them, because if you choose none of them here, then you'll have to choose 3 points there, and that wouldn't give you a triangle. So these are the only cases that you have, and you've got 16 such triangles. Now, at this stage, I just want to say something. Okay, I'm going to use the same sheet that I chose before. Just ignore the question at the top. Now you'll notice when we wanted to choose 2 points from 4, we saw that there were 6 ways of doing it. Now I just want to expand on that idea. So we just saw in how many ways can 2, we wouldn't talk about points, we'll just say objects be chosen from 4, right? And the answer was, we saw, is 6. We saw this just now. When we choose 2 points from 4 points, we saw what they were. Now, you'll notice that the way we did it was, we had AB, AC, AD. So what we had was, we had, if you just fix A, then you got 3. And if you fix B, we had 2, BCBD. And then for C, you have 1. Right? So you can always do it like that. Right? If you had 4 points, it's 3 plus 2 plus 1. Or if you like, 1 plus 2 plus 3. And if you had 5 points, it would be a similar kind of a thing. For 5 points, or 5 objects, they need not be points. It will be 1 plus 2 plus 3 plus 4. Try it out and you will see. If you've got A, B, C, D, E, then you've got AB, AC, AD, AE, like that. That gives you those 4. That's where this 4 comes from. And then you can continue like that to get this. So in general, if you had n objects, then it will be 1 plus 2 plus 3 plus 4, all the way up to n minus 1. See, because with 5, it landed up with 4. You have to count 4 numbers. So in n objects, you count to n minus 1 objects. Now, this, we have done this many times. The sum of the first natural numbers, like for instance, 1 plus 2 plus 3, all the way up to 100. 100 is 100 times 101 divided by 2. We've done this before. So here, this will be n minus 1 times the next one. The one after n minus 1, if you add 1 to this, you'll get n. Right? This is the number just before n. And that sum is n into n minus 1 over 2. So this gives you a very, very important formula, right? Which says the following. It's used, we'll come across this thing many times. And the question is the following. In how many ways can one choose 2 objects from n objects? That's the question. And the answer is, got a formula for it. We just saw it now. Answer is n times n minus 1 over 2. Not n into n plus 1, right? It's n into n minus 1 over 2. So please remember this. So if I had 40 objects and I want to choose 2 from there, it'll be 40 times 39 divided by 2. Okay, so that's a very important fact that I want you to remember. Okay, so I'm not sure whether we're going to come across that again, but please remember it nonetheless. Okay, here you got how many two-digit odd numbers can be made using the digits 1, 2, 3, 4, 5, 6, 7, 8. If each digit can be used only once in a given number. Okay, you got quite a mouthful there, but if you do it the way I'm telling you, or the way I told you, you'll see it's not difficult at all. All right, so you want to choose two-digit odd numbers. So in other words, I must create a two-digit number. And this number could be starting from 10, going all the way up to 99. Those are the only two-digit numbers, right? Now, you can choose them only from these 8. So you're not allowed to choose 0. You're not allowed to choose 9. Because those two are also digits. All right. Now, each digit is to be used only once. Oh, but it's odd numbers. So they must be odd. Okay, now that's interesting. It means that the second number here, right, it's restricted. The last number, it's an odd number. So what can go in here? From these numbers here, you can have 1, 3, 5, or 7. You're not allowed to put any of the others because an odd number will always end in an odd number. It cannot end in an even number. So there are 4 ways in which you can put a number in this box here, the units digit, right? And now the question is, how many digits can be, so in how many ways can you put this? Now here, there's no restriction. You can put an odd number or you could put an even number, but each digit must be used only once in the given number. See? So it means if I choose one of these odd numbers, say 1, right? I'm not allowed to choose 1 again. I'm only allowed to. So in other words, the second choice can come from only 7 numbers, right? The same thing, if I choose 3, the second choice can come from 7 numbers. So there are 7 ways of choosing this one because you're not allowed to choose the one that you already chose. So therefore, the answer immediately is 7 times 4 because that is the first counting principle. Right? The second, this time you will say the second digit can be chosen in 4 ways. And having chosen the second digit, the first digit can be chosen in 7 ways. So therefore, altogether, you got 7 times 4. This is not the number 74, please. Right? This is my box. The number of ways in which you can choose the tens, the units digits, and the number of ways in which you can choose the tens digits. Okay, so now this is a nice application of what I just said earlier on. Okay, so let's just get on to the next problem. I have 5 books, one of each color. How many ways can I place them in a row? Okay, I presume the colors are all different, so they are distinguished. Now this time you've got 5, and you're going to put 5 books in a row. All right, so maybe you're going to put them in a shelf. Like for instance, you're going to put them all next to each other. You're going to put these 5 books like this, and those 5 books can be placed like this. Now you got, if you name the books as A, B, C, D, E, so if you name the books as A, B, C, D, E, or call the books A, B, C, D, E. We'll just use symbols for the books. Don't really have to know the titles. And now you're gonna place them on a shelf. There are many ways of doing it. You can put a C here, and you're gonna put a B here, you put a D here, you can put E here, or A here. So that's one of the possibilities. And like that, now you can see there are lots and lots of ways in which you can place them in this row, right? So that the question is now, in how many ways can you place these 5 books in a row, right? Now, we're going to do it the way we've just described. I'm not going to put, in this thing here, I'm not putting books. I'm going to put numbers. The numbers I'm going to put are the number of ways in which you can place the book in any one spot. So in the first spot, right? Suppose I've got the 5 books with me all stacked up on a table. And you're going to place them. And place 1, 2, 3, 4, 5. And you'll take the first one and you'll say, well, where shall I put it? Okay, I can put it anywhere. I've got 5 different ways in which I can place it. So the first book can be placed in 5 different ways. All right, so I'll place the first book. Out from the first book. I've got 4 books left. Now, I'll take this next book here. And where can I place it? I can place it anywhere here. I'm not allowed to place it there, obviously. The first place is taken. So the second book can be placed in any one of 4 different ways. Right? So that gives you 20 different ways in which you can place the first 2 books. Right? If you want to know what the 20 ways are, it's A, B, A, C, A, D, A, E, or you can have B. You can put B in the front, B, A, B, C, B, D, B, E, and so on. So you've got 5 times 4 ways of doing that. All right. Now, having placed the second book, the third book, you can place it anywhere here. So there are 3 choices. The fourth book, you can place it in only one of those 2. And once those 4 places are chosen, then the last book has to go there. Okay, these are the number of ways in which you can place those 5 different books. So the answer is 5 times 4 times 3 times 2 times 1, right? Normally, we write this thing as 1 times 2 times 3 times 4 times 5. That's 120. When you multiply all these numbers, you get 120. 4 times 5 is 20, 2 times 3 is 6, and 20 times 6 is 120. Now, let me just pause here for the moment. This number here is very important. It's a product of all the numbers from 1 to 5. And we have a symbol for that. When you multiply all the numbers starting from 1, and the answer to this problem is 120, by the way. Okay. If you multiply all the numbers from 1 to 5, then we write this thing as 5 with an exclamation mark outside there. So 5 with the exclamation mark. You read this as 5, and instead of saying exclamation mark, you say 5 factorial. Now, this is not as if you're so surprised to see the number 5, right? No element of surprise here. This is a mathematical symbol borrowed from the symbols in the English language. And we read this as 5 factorial. And this, by definition, is 1 times 2 times 3 times 4 times 5. And as we saw, this is 120. So in general, you could have had 1 times 2 times 3 times 4, all the way up to n, right? And that is written as n factorial. Right? So whenever you see anything like this, you read it as n factorial, and you must know that it's 1 times 2 times 3, all the way up to n. Okay, so in this problem here, what we saw is that the number of arrangements of n objects is n factorial. Right. If you had five books, how many ways can you place them in a row? That's an arrangement. There are so many different ways in which you can arrange them. Now, how many ways can you arrange them? We saw the answer was 5 factorial. And the same logic applies, right? Only then you will have n boxes because you've got n books or n objects. And then you will say the first one can be placed in n ways, second one in n minus 1 ways, and so on and so forth. In the end, you'll have to multiply all the numbers from 1 to n, and it's n factorial. So this is a nice fact that the number of ways in which you can arrange n objects is n factorial. Right? It helps a lot in counting because you got to. It's like a formula. Okay, so as I told you, this most of these problems are about counting. Now, the next problem is you wish to create a string of 10 numbers using only 0 and 1. Right? In how many ways, how many such ways, numbers can you create? All right, now you got 10 numbers. So you have to choose to put 0 or 1 in each of those boxes. So if you think of these as boxes the way I do, now you need to divide this into 10 units. So I think I'm going to just use this. I can just divide halfway here, then I can put 2 here, another 2 there, put another 2 in the middle here, and 2 there. That gives you 10 boxes. Right. Now, you want to create a string of 10 numbers using only 1 and 0. Like, for instance, you can have 1, 1, 0, 0, 1, 1, 0, 0, 0. How many have you got? 4, 5, and 9. And you can put another 0 if you like, yeah? So that gives you a string of 10 numbers involving only ones and zeros. And you can see I have to make, each time I put in a number, I have to make a choice. What do I put here? There are 2 ways in which you can put that. You put either a 0 or a 1. And here you can put a 0 or a 1. For instance, if I had just 2, I could have 1, 1, 0, 1, 1, 0, or 0, 0. You can see there are 4 ways. The first one can be chosen in 2 ways, 1 or 0. And for each choice of the first, I've got 2 of the second. So that's how you get 2 times 2. So there are 4 ways in which you can just put the first 2. And like that, if you proceed, for each of these 4, you got another 2 here. And it goes on. You have to each of these boxes can be filled in 2 ways. And altogether, if you want to count how many there are, it'll be 2 times 2 times 2, because each one of those boxes can be filled in 2 ways, right? So the answer is actually 2 multiplied by itself 10 times. And you know what that is, 2 to the power of 10. Right? I don't know how many of you know what this is, but it's 1024. So the 1024 boxes like this. You get this kind of thing in a TV screen. You'll see, I think they call them pixels. On a TV screen, each point does, I think, I forget, but it's a large number of points. And at each point, you can have a switch, which is on or off. And that's when the light comes through. And the switch is on or off. And or it has a specific color to it. So each point there is a certain color, and you want to know how many different colors have you got on a TV screen. You can imagine it's quite a atrocious number, because you can on a TV screen you can put, I don't know what, I'm not too sure, but I think you got 4,096 pixels or something, and each one of them has to be filled with a different color, maybe 5, 6 colors. So you have to multiply all these things together. Anyway, so that's this problem. Also, if those of you who are familiar with binary numbers, this is what you call a binary number. So a number which has got only zeros and ones in it is called a binary number. And it's a very, very important concept, what you call binary arithmetic, because the 1 can stand for a switch, which is on, and the 0 can stand for the switch, which is off, right? So in many electrical circuits, either a switch is on or off, and to different colors, if you change them randomly, you'll get all kinds of configurations, which helps us a great deal in electronics. All right. Now, Como Hello just entered the waiting room. Khotso, don't admit him. We did say that people must enter. If anybody enters after 5:25, they're not allowed in. But we have been a little bit kind today. We allowed a lot of people who are coming in at random times. Don't admit this person. And hopefully that'll send a signal to all the others that if you come after 20 past 5, I think it's 20 past or 25 past, you're not allowed into the room. Okay. We're going to follow that policy in future. There must be some discipline here. Okay. How many positive 4-digit numbers between 1,000 and 9,999 are there that are divisible by 5 with every digit even? Okay, now this should be quite easy, because we've seen the way to do this. You got 4-digit integers, so we're going to fill in 4 places. I'll have to fill in 4 boxes, and I need to count. So you're going to put a 4-digit number into this, and I want to see what digits can I place in here. And the question now tells you the following. These are 4-digit numbers. So in other words, if it's a 4-digit number, digits are coming from 0 to 9. So in these boxes here, you're going to only put 0, these numbers here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that gives you 10 numbers altogether. 1, 2, 3, 4, 5, 6, 7. 7, 8, 9. 9 plus 1 is 10. So you can put any one of these 10 digits. These are called digits. All right. The 4-digit numbers. So just bear in mind, you can't put a 0 here, because otherwise it's not a 4-digit number. So you can only put the numbers which are 1 and more. And they say, yes, between 1,000 and 9,999 are there. Now they are divisible by 5. All right, let's start with that. If it's divisible by 5, the last number can be 0 or 5. Right? The numbers which are divisible by 5, the same as saying the numbers which are multiples of 5 can only end in 0 or 5. When you learned your 5 times table when you were little, you enjoyed the 5 times table. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So it's very easy to know the 5 times table because the end in 5 was 0. Now, but every digit is even. Ah, there's another thing here. So you can't put 0 because 0 is an even number. So you can only put 5 here. You can only put the number 5, but I'm not going to put the number 5 here. I'm going to put 1. It means I have just one choice for the last digit. I have only one choice, and that is 5. Only 5 can go in here. Right. Now every digit is even. So in this place here, let's go to the left. You can put 0. That's even. A teacher once asked me, why is 0 even? My answer was, well, if you add 1 to it, it becomes an odd number. That's a very good answer to why is 0 even. So you got 0, you can put 0 or 2 or 4 or 6 or 8. Those are the only possibilities for this. So there are 5 possibilities here, right? You could put any one of these. Here too, there are 5 possibilities. Every number is even. But here now, again, there are 5 possibilities. Oh, but you can't put 0 now. You're not allowed to put 0 here. So you can only put 2, 4, 6, or 8. There are only 4 ways in which you can fill the first number. So these give you the number of ways in which you can fill each box. And that is the strategy in solving these problems. So the answer is, once you have done that, then you simply have to multiply all these. 5 5s are 25, 25 times 4 is 100. So there are 100 numbers with every digit even between 1000 and 9999. You can see how powerful this principle is. This is a second countable principle. The first count, you only got 2 boxes. Second count is you can any number of boxes. All right. Why? Because if you were to write down all these numbers, you'll have to write down 100 numbers all the way from 1000 to 9999, and that's an extremely tedious process. Right? By the time you finish, you probably will die of old age. All right, so let's get to the next problem. So the answer to the last question was 100. Okay, so the next problem is the following. Again, it's the same kind of a problem, but there are so many different variations to this. In how many ways can 5 students, again, use the number 5, line up in one row? So it looks very much like the books problem. But they say if students B, C, and D must stay together, all right, they are going to line up in a row. But I must have B, C, and D must be together. So you got, let's just try that. Oh. So you're going to place these 5 guys. Like that. But you must have B, C, and D must be together. So I could have had B, C, D here. The first 3. Let's take that. B, C, D there. Now, then A and E, you could have had A and E or E and A. Right. So this particular choice you've got two ways in which you can place the remaining two. Right? Now, I could have had, instead of B, C, D, I could have mixed these guys around, right? I could have had B, D, C, starting with B, or I could have had C, B, D, or I could have had C, D, B, starting with C, or can I start with A, I'm sorry, starting with D, I could have had D, B, C, or D, C, B. So these three can be arranged in 6 ways. Right? You could have done it as I said earlier on, it's 1 times 2 times 3, you see, so that's 6. So all there are 6 ways in which you can arrange these guys. So with B, C, and D in any order in this position, right? This gives you the, for each choice of these, there are 2 choices to finish off. You can put AE or EA. Right? So there are 2 choices. So that gives you 12 altogether. For each choice of this, you got 12. Right. But now they say only that they must stay together, but they don't have to be staying where I just put them now. Right? They could have been placed. They are only supposed to be together. I could have put them together here. I could have put them together here. The second, third, and the fourth. Right? So there'll be another 12 for that one. Right? Or I could have put them in the last 3. There'll be another 12 there. So I could have placed them here, or there, or there. And for each of these, there are 12 different arrangements. And therefore, the answer is 12 plus 12 plus 12. Oh, 12 plus 12 plus 12. That is 36. Or 3 times 12. You see? So you could have, instead of writing all this down, okay, but look, this is working from first principles. So you can see exactly where the 36 is coming from. But if you're a little bit more advanced, you can say, well, I could have put B, C, and D in 3 different positions, right? Then I could say, right, for each such position, I can interchange B, C, and D in 3 factorial ways. And for each of these 3 factorial ways, I've got 2. The other 2 can be arranged in 2 ways. So therefore, I'll have altogether, I'll have 3 times 3 factorial times 2, which is 3 times 2 is 6, and that is 6, gives you 36. You could have done it like that. But that is when you're at an advanced level, you can think like that. But here, you can work it out from first principles and see exactly what's going on there. Okay, let's get on to the next problem. Now, the next problem is all the words that can be formed from the letters A, H, M, S, T are written down in alphabetical order and are numbered 1, 2, 3, 4, etc. Which number in the list is the word maths? Oh, now this looks like quite a demanding problem. But again, you only use formulae when you're forced to. Most of the time, you will use your common sense and try to understand the problem, and then try to answer the question. So you're numbering these things 1, 2, 3, 4, 5, and so on. And right towards the end, you got 50. Oh, Why do I choose 50? There's no reason to choose 50. Let's just knock that out. Okay, so what is the very first one? You're writing the words, the letters of maths in alphabetical order. So you'll put A, right? You're creating a dictionary, in other words. And the next one is H, M comes after that, S, T. Also, that's nice. They give you this in alphabetical order. But the next one will be in a what? It'll still be A, H, M, and you'll have TS, like that. And the next one will be A, H. Now, we finished M as the third letter. This time, you'll put S as the third letter. And then you put MT. And the next one will be AH, STM, and so on, right? Okay, so what happens here is that you have to write down all the numbers, all the ones which start with A. All right. So how many of these letters start with A? It means that I have to see how many arrangements have you got with H, M, S, and T. Right? If all of them start with A, then you look at all the possible arrangements with H, S, M, and T. So you'll have, starting with A, there are the number of ways in which you can arrange 4 letters, as I told you earlier on, here's a good application, is 1 times 2 times 3 times 4, which is 24. Right, so if you arrange all these in all the possible ways, then you've got 24 ways. The first letter can be chosen in 4 ways, next one in 3, next one in 2, next one in 1. So you multiply all of them together and you get 24 ways. All right. We need to get down to maths. Which number is maths? So the first 24 start with A. The 25th one starts with H. You're finished with A now, right? 25th one starts with H. And now the very first one, you have to put A, M, S, T in that order. Right? A, M, S, T. And you do the same thing with H. And you've got another 24 here, which starts with H. Right? So you've got 24 plus 24, which is 48. So 48 start with A or H. Right. So once you finish off with A and H, you're creating a dictionary. The next one is M. Now we are there now, because we want to get to this one here. Right? Now, the very first one is number 49. So if you have M, you'll have A, H, S, T in that order. Fortunately, they've given us this in alphabetical order. So you got A, H, S, T. Now let's go to 50. You'll still have M, A, H, and now you'll put T, S. That's 50. 51 will be M, A. Oh, now the H's are finished. Yeah. You have to put S first and then put HT. Then 52 is MA, STH. That's 52. And then 53. Okay, we're finished with MAS. So you'll have to have MA, MAS. So now you go MAT. Right? And then you'll have H and S. Oh, there it is. You got your maths. Right? The MAT, H and S. So the answer is 53. That's the number to the word maths. It's all common sense, guys. You just count, but there must be some systematic way in which you are doing it. And you must understand the question and then do the counting. But don't just read the whole question without understanding what it is, looking for some formulae. That's not going to help you. We don't do maths like that. Only sometimes when you come to a situation where you can use a formula, then do so by all means. But generally, you just use your brains. See? Just use your common sense to get to the answers. All right. So now here a set has 300 elements. How many subsets does it have altogether? Now you have to know what you mean by subsets and sets and so on. Let's take a simple case. I don't know whether you have done sets at all in your lifetime. Suppose the set has 3 elements. I'll make it 2 elements. Let's call it AB. So what are the subsets? The subsets are smaller versions of the same set. You just take some elements from the set and make a new set. So you could have had just taking the subset which consists only of A, or the subset which consists of only B, or you can have a subset where you got both A and B. And you might say, well, these are the only subsets. Either you got 1 element or 2 elements. But in sets, you also include the subset, which is the set which has got no elements. It's written as the symbol here, like that. Right? And that is what we call the empty set, the set which has got no elements at all. Okay? So we must include that, because that is also a subset, the subset which has got no elements. So the answer here is 4. Okay. Now, if you had a set which has got 3 elements, somebody has got his mic on. Can you please switch your microphone off? I think it's Ovayo. Ovayo, can you just switch your microphone off? So if your set has got 3 elements, you can do the same thing. Count you'll have to count the empty sets. Start with no elements, then start with 1 element, right? No elements is one of them. With 1 element, there will be 3 with 1 element, A, B, or C. And then with 2 elements, you get another 3. And if you got the whole lot, A, B, C, then there's 1, and you get 8 here. Right? If you try 4 elements, it becomes a little bit more difficult. You'll get 16 subsets. And then you see a pattern here, because this is 2 squared, and this is 2 cubed, and this is 2 to the power of 4. So it looks as if you've got a set having 5 elements, you can predict that it will have 2 to the power of 5 subsets. But this is only by guessing. It's not a very rigorous way of making that conclusion. But it turns out that is the correct conclusion, right? Although you can't say because it works for 4 or 5, it's going to work for anything, right? So if you got 300 elements, the answer is 2 to the power of 300. subsets. It's an extremely large number, 2 to the power of 300. And that is the answer to the problem. How many subsets does it have altogether? Okay, if I got time, I'll come back and try to prove this. And I told you that this is just guessing, but you can actually prove it. But it might take a little bit of time. So I'll only do that if I do have time. Okay, so that answers that question. So we need to get to the next problem. And here is how many 3-element subsets does a set having 8 elements have? Oh, now this is a little bit, it's a new kettle of fish. If I had 2-element subsets, in other words, a subset having 2 elements, it's the same as choosing 2 elements from 2 objects from 8 objects, right? If I had that question, the answer is, as we saw earlier on, remember we said n into n minus 1 over 2. We discussed this particular case. We said if you are choosing 2-element subsets, then the number of ways of choosing 2 objects from n objects is n into n minus 1 over 2. So in this case here, for eight objects, you have 8 times 7 divided by 2. And that is 2 goes into 8 4 times, so it's 28. But that's not the question. The question is how many 3 elements? And we didn't solve this problem. But I can tell you it's very similar to this. Right? You can write this as 8 times 7 over 1 times 2. This is the number of 2-element subsets. But the number of 3-element subsets is very similar to that. It's 8 times 7 times 6. Right? But at the bottom you have 1 times 2 times 3. And so there is a very nice pattern in this. See, the number of 3-element subsets that a set of 8 elements have is you start from 8 and you go down, or maybe you put the denominator first. 3 elements, you got 1 times 2 times 3, but then you write down the same number as what you got at the bottom. You got 8 times 7 times 6, you stop there because there are 3 here, you have to have 3 there. So 3 times 2 is 6. 6 cancels with that. And 8 times 7 is 56. So the number of 3-element subsets is 56. So that's the answer to this question. Okay, so here is a fact. Instead of using 3 or 8, let me use general symbols. The number of, I'm going to say R. In our example, R is equal to 3. R element subsets that a set of n elements. Instead of 8, I'm going to put n. So I have a general formula. Is, I've just told you, but let's just do this in the general case. So what we have here is a fraction. Now, I told you for 3, I'll put on 1 times 2 times 3. You do exactly the same thing. it's 1 times 2 times 3 up to R. See? Up to R. And then at the top, you've got, instead of 8 there, you've got N. You start with N. And you reduce it by 1. Reduce that by 1 again. N minus 1. N minus 2. But you'll only go up to, the top part will have R factors. Right? So the numerator has R factors. The same as the bottom. See? So this is a very useful thing. It's not in your school syllabus, but in Olympiad problems, this comes up sometimes. Number of R element subsets that a set of N elements has is that number. Okay. It's got a lot of applications, this fact, because you can, it's a way of counting. Look, for instance, now, I'll just give you an interesting example. If you say, in how many ways can 6 numbers be chosen from 50 numbers? Now, you might recognize this is the same as the lotto problem. People have, I don't know, I've never played lotto. I think it's 50 or 49 or something. But you've got a large number of numbers and you want to choose 6 numbers. And people, they just say, choose 6 numbers. You know, whatever 6 numbers are, they say, oh, these are my lucky numbers. You know, it's my dog's birthday or something, the number of crocodiles I killed 3 years ago. So they'll write down all these numbers and they'll say, these are the 6 numbers that I choose. Right. And the answer here, we can answer this. We can actually find out how many lotto tickets you have to buy to win. Right? Because it'll be the total number of ways of choosing 6 numbers. You at the bottom, you have to put 1 times 2 times 3 up to 6. You have to choose 6 numbers. And now you start from 50 and you only have come down. I think you land up at 45. 1, 2, 3, 4, 5, 6. Yeah. All right. So you have to multiply all those numbers and divide it by this. And if you cancel it, you got, say you got 6. 6 goes into this 8 times. 4 goes into 8 2 times. This 2 is cancelled off here. And you have 3 goes into 15. This. So it's a product of all these. 50 times 49 times 46, 47 times 46 times 15. And now this is approximately, this is 50 squared, which is 2,500. And 47 times 46 is approximately 2,200. And you're going to multiply that by 15. You can use a calculator to get the exact amount, but this is already, got 4 zeros here. 25 times 2 is 550. So times 15. And you can see it's going to be 5.5 million times 15. That's 75 million. You have to buy 75 million tickets. I'm not sure whether this is the correct, the calculations are correct. Oh, there's a 5-year also at the bottom. All right. So it's actually about 25 million. So 5 goes into this. So it's maybe around there. But that's a large number, boy. You have to buy 25 million tickets. The population of South Africa is around 60 million. So it means that if everybody in South Africa buys 2 tickets only, then you still got no way of winning it because the winning ticket will be in the other side. All right, so that is an interesting problem. We get on to the next problem. And so here we got, and how many paths are there from A to B? Oh, this is B here. B here. From A to B. If you can move downwards and to the right. Okay, now this is a common kind of a problem where you count the number of pathways you can draw from one point to the other. Like for instance, I can move to the right and downwards. So I can do this, come down here like this, and then go down there. I can't go up. I can go this way. I can go to the right, then I can go down, I can go here. So that's one possible pathway. So like that now, how many different pathways have you got? You can try it out, but it can be very complicated because you don't know whether you are repeating a pathway or not. That's a problem. And you can count it because it's a small number. But there is a nice logical way of doing this thing, and just listen very carefully because we link it to we look at just one particular square from here. And I'm going to assume that I know how many paths there are to this point here and how many paths there are to this point. And at this point, I'm going to put the number m here, which says number of paths to this point here. Let's call it x. From the starting point. Right? And then this one here, let's call this y. And there's a number here, right, which we're going to put there. Is equal to the number of paths to this point, to y. So in other words, at these vertices, I put a number which says the number of paths from that point to that point. Now, like for instance, now from A to get to this point here, there's only one way of doing it. I can only go that way. I can't go down and come up again. I'm not allowed to do that. So there's only one way to get here. Even here too, there's only one way. From here to here. And even here, there's only one way. See? And if you go down also, there's one way here. One way. So these numbers here tell you the number of ways in which you can get to this point. But now, suppose I look at this one here. Right? To get to this point, I can go that way, like that, or I can go that way and that. Right? So there are two ways of getting it here. It's actually 1 plus 1 because it's the number of ways you can get to this place, and from here to here, there's only one way to do it. So it's this from here to here, if it's m ways, and from here from here to here is n ways, and from this point to this point, there's only one way of doing it. So altogether, you'll have m plus n. See, so this number here can be worked out because the m ways of getting there, together with coming from here, you can to get to this point, you can come from there or from there. So you have to add those two possible pathways, right? And you'll get m plus n. So that's how we'll put a 2 here. Now, once I put a 2 here, 2 and 1 will give you 3. 3 and 1 gives you 4. See, they're the opposite, the diagonals on this side, like that. And here too, I can put 1 plus 2 is 3 here. And then in this little square, I got 3 plus 3, which is 6. And at B, I got 6 plus 4 is 10. So there are 10 pathways. And the idea is once you got these two, you can use those two to calculate that one, the one underneath and to the right of this. And bearing in mind that you already have ones in several places. And from there, you can build up to get to any point you like in this picture. You can use the same principle to have a 4x5 grid or whatever, and you try to go from one point to the other, and you do the same thing. It's very easy, the actual method, because all you have to do is to tag each vertex. Okay, so that takes care of that. And the next one, okay, so you've got an assignment here. This is your assignment for this week. All right. It's quite a challenging problem, and I wish you luck in this thing here. It's got 13 marks. So you've got 25 horses, and you want to race them. What is the minimum number of races needed? So you can identify the 3 fastest horses, right? You don't know how fast they go, and you don't have a timekeeper or anything like that, but you can race up to 5 horses at a time. Can't race more than 5. So you must try to race 5 at a time and identify which are the 3 fastest horses, right? So you have to do it in several trips. But how many races do you need altogether to identify the top 3 horses? And you need to know the smallest number of races that you need to identify them. So that is your problem. It's going to be quite a challenging problem. I wish you luck in that. Okay, now it's already 1837, and I can, if those who want to go, you can go. But I want to just do that one to explain why you got 2 to the power of 300. I think I had it here somewhere. Yeah. All right. Now, I want to count how many subsets there are. And there's a very clever way of doing it. Let me just put down some boxes here. All right, so I got 1, 2, 3, I got eight elements, and I want to create a subset from 8 elements. So let's just name the elements. A, B, C, D, E, F, G, H. All right, so what I'm going to do is the following. I'm going to imagine that these are 8 boxes, and underneath each one of them, I have a light bulb. Oh, I'm terrible in drawing. Anyway, I have a light. These are all supposed to be light bulbs. Okay, this looks like a man. Yeah, this looks like a tree. But I was hopeless in drawing. Anyway, the original light bulb, oh yes, it was like this, something like that. Anyway, suppose at underneath these boxes, you got light bulbs. You can't see them, but you got 8 boxes. And every time I put something into a box, the thing lights up. If I don't put anything, it remains dark, right? So a box is either lit up or it's dark, right? Depending on whether I put something into the box. Now, what something am I going to put? I'm going to put this something where I'm going to choose my subset. Suppose my subset I choose is CFH. So what I'm going to do is, this is your ABC, A, B, C, D, E, F, G, H. So I'm going to put my C, F, and H. I want to put C inside here, and I'm going to put F inside here, and I'm good. Now, the moment I do this, these three light up, and the others are dark. See? So like that, now you can take any subset and put them inside there, and those particular boxes will light up, or those will be, and the rest will be dark. Now, each time I have a subset, I have a lighting up of the boxes, right? As I explained to you. And of course, each time, this, I'll have to say this thing here, but you might not understand why I'm saying it. But each time I have a lighting up, suppose, suppose you have the bulbs. Something is happening here. Anyway, so suppose, for instance, the certain bulbs light up here. Suppose, trying to choose. Oh, there we go. If I have these lit up, for instance, those are lit up now, then it means that I have chosen the subset B, D, F, G. So in other words, there is a correspondence between a subset and the lighting up of boxes. Now that is very crucial, because now if you want to count how many subsets there are, I'll repeat this. If you want to count how many subsets there are, then you have to count in how many ways can this box be lit up. To count the number of subsets, it's the same as counting the number of ways your box can be lit up, right? Now, the box can be lit up in only two ways, either dark or it's bright, any particular box. See? So either it's light or it's dark. So now if I want to count the number of ways, this time I'm not putting objects inside here. I'm counting the number of ways a box can be lit up. And I can, this thing can be either dark or light. So it's either dark or light, here dark or light, and so on. So we have to choose, it's either dark or light, and that each time I choose something, it gives you a subset. But now, in other words, each box can be filled in only two ways. So therefore, the number of subsets equals number of ways the boxes can be lit. And that is equal to 2 times 2 times 2. And depends how many, we got 300 boxes here, because you got a set which has got 300 elements, 300 times. And that's 2 to the power of 300. See, in general, if you got n elements in the set, then the number of subsets is 2 to the power of n. Okay, so that will explain where the 2 to the power of n comes from. I hope you understood this. It's a little bit subtle, but I'm sure you'll be able to understand it. Okay, so that brings me to the end of this session. Thank you very much for being here. I just want to stop my sharing. And okay, half the people. Yeah, thank you very much for remaining till the end. I hope you learned a few things, especially counting. And if you can count properly, then you've got a whole section in metric where you can get full marks. And what we have done is even far more difficult than some of the problems that you get in metric. So hopefully that helps you in your schoolwork. But there are some important things that I've said. The number of possible subsets you can have of a given set, one, the number of ways you can choose two elements from a set, and again, the number of ways you can choose any number of elements, R elements, from a set. Those are some of the things we have learned. And then also, if you've got M ways of doing one thing and N ways of doing another thing, then you can do it, both of them together, in M times N way. That's the first counting principle. And if you've got several boxes, that's the second counting principle. So there are a couple of interesting theory, the background theory to this. And we hopefully we learned a few things. Okay, if there are any questions, I see in the chat group, there are some things. Can we have a link where you can get practice problems similar to Olympiad problems? Well, I can't give you a link to that, but what you can do is go into the SAMF website. You can go into the SAMF website and www.samf.ac.za. That is your SAMF website. And there you go eventually to Olympiad problems, or SAMO problems. Sorry, bad writing here. This screen is not very helpful. Questions and answers. And there you got the last umpteen years, maybe 12 years of questions, large number of questions. And they have the answers as well. But the answers not as detailed as the way I say it. And they need not be the same as mine, because I tackle my problems differently. But it's a good place to go to. And there you can identify